good morning or good noon. So that's the agenda of my talk. So in the second part of my presentation, I'll go to some more visionary stuff of why do you want to combine global data with proprietary data, what it takes to do so, how analytics on big knowledge graphs can help you do it, and what GraphDB offers to enable this. So I started Ontotext back in year 2000. Back then it was like semantic web pioneer thing. No longer the case for quite a while because, as many of you probably know, around 2007-8, semantic web was a bit out of fashion. So we went doing a number of other things that you just see based on the same technology stack and standards. We have probably half of our clients are here in London, and then we have quite some clients in New York, and the rest is the long tail. We had the chance to do a lot of research. We got financing to do a lot of more research. We've been on all sorts of web semantic technology events forever, and the industry bodies. But what we're actually trying to do, and what came up as a mission of a company that started as a technology company, and we had to take our time to figure out why we are doing this. So most of the usage is enterprises, and essentially helping enterprises combine the diverse data and link it to content and extract information from unstructured content. So technology-wise, we do graph database and text mining. We've been doing large-scale symbolic reasoning, like the normal how-to things, description logics, many other things. Nowadays, we are more into we are shifting more towards statistical inference, machine learning techniques. And when you deal with data and enterprise data for so long, you figure out that, well, technology is good, but you get to know the data. There is no technology that's good for all sorts of data, so it requires good tuning for specific domains. And we've been spending quite some time in dealing with company data, working with publishers, and also life sciences, pharma, government. So we are best known for our database engine. It's called GraphDB, and it is like in the top graph databases. You see in this ranking, you have very few triple stores, probably only Virtuoso and ourselves. We like analytics. It's quite a lot of fun. So historically, we did a lot of analytics. 2 years ago, back in June 2016, we predicted Brexit. So we did. We published a white paper on 14th of June, a week before Brexit, based on analysis of 1 million of tweets, saying in Twitter, based on all sorts of analytics, like number of tweets, and then number of impressions, number of interactions, influencers, number of people who follow this and that. So it was like 5 or 6 different metrics, and it was clear cut that the support for Brexit in Twitter alone was like twice higher. Let's go. And this was a week before that. So
did you short the pound?
Sorry?
Did you short the pound?
No, it was me. But in fact, most of the time, in order to get to these fancy things, you have to do a lot of heavy lifting in terms of just putting the right types of data together, reconciling, linking, cleaning, and that's what most of our technology actually does, to allow most of the time other people, data scientists, to do the fancy stuff on top of it. What's unique is that we have plenty of vendors in the database space. We have plenty of vendors in the text analytics. There are very few companies which do both and know how to combine both very well. We had the chance to do a lot of advanced research when we started, and then in the last 10 years we've been actually taking care to productize these fancy algorithms and technology and inference and machine learning to make it robust enough to back like Financial Times website or BBC website or quite a number of others. So that's roughly some indicative selection of our users. You see many of them being in the publishing. We have 3 out of the top 5 science, technology, medicine publishers. And I'll speak a bit more on BBC because this was sort of the first and like the pioneer project that demonstrated that this technology can be used in media and publishing. And nowadays we're more into dealing with business information for people like Standard & Poor's, Nikkei, and others. So enough about it. So if we have to start with the basic thing of like what sort of technology, what sort of machinery you need to put different types of data together. One use case is imagine you want to identify suspicious patterns in relationships between companies. So you can put together a company database that is telling you that Big Bucks Cafe is located in Seattle, and it controls Global Investment Inc. and it controls my local cafe. And then you can have this linked to a geographical database that knows that Seattle is part of Washington, part of US, and West Bay appears to be district in Cayman Islands, and so on and so forth. So one application of this technology using graphs and connecting data from different sources is to make it very easy to detect patterns like this. You have a company in US that controls another company in US through a company in an offshore zone. It could be just fine, but there are plenty of people who want to know these patterns. And with this technology to do it right, you should be able to put the company data with the geographic data together, and then do all these small steps of inference that after that make queries really fast to allow you to do this kind of pattern matching on top of several billion facts in a matter of a second. So that's where we sort of get started. To support this use case, you should be able to ingest the data from different sources. So it was probably a year ago when I tasked our team, well, look, I want to ingest CSV as easy as in Excel. You know, in Excel, you open a CSV, you say, I have header line, I don't have header line. You gotta use this column as a date and this column as a number, and there you go. We did this integrating OpenRefine, which allows you to preview your table data before you load it in the graph. Do some analytics of like, see what are the most popular values in a specific column on the fly, really, directly. And then the next task is, again, as part of this ingestion process, to reconciliate data. So if you have airports, to be able to reconcile cities and countries to entities that you already have in your knowledge graph. So there is a very simple interface that allows you to say, well, I want to reconcile column city to the class city, and there you go, and you get some candidates you can choose and move forward or add new values. Quite often, to make this reconciliation right, you actually need to get involved some other columns to give you more context, so that matching is more likely to happen. So St. Anthony, there's plenty of St. Anthony's all over the world, and to choose the right one, it helps a lot if you use the country column. And it's not rocket science, but having the tooling that allows you to do it like as easy as in Excel is quite a big thing. So you can say, I also want to use the country column with matching it to whatever values. And then you can use country to reconcile city and city to reconcile airport, and make these combinations again live. Okay, you got your graph. So you ingested it from here and there, you loaded geo names, you know that loaded a few other data sources, you put it in. You should be able to explore it. You'll see a bit of this in the demo. Being able to properly search and pick up concepts in a big knowledge graph, speaking of billions of things, is really not a trivial thing. And we have out-suggest that use cognitive analytics to figure out which is the best one, at least the most important one, the one that is most likely that to search for. You see it in action, then you can visualize, of course, one node at a time, and expand, and so on, and then see some features, do some Sparkle queries, and that's sort of trivial thing. It helps if in the Sparkle editor you have the kind of auto-suggest, because in a schema where you integrate the data from multiple sources, you are very likely to have like hundreds of classes and properties that most of you wouldn't remember easily. So for some of the demonstrations, I'll use a service called FactForge. What it is, it's the English version of DBpedia plus geonames plus the mappings between these guys, some company data from different sources, and a lot of news metadata, like more than 1 million news articles annotated and linked to this knowledge graph. So altogether we are speaking of like 2 billion triples. And that's the point where I'll make the first demo, figuring out what do you have in a big knowledge graph like this is not easy, because in this case, in this demonstrator, we have 1,400 different classes. 1,400 different classes. So figuring out what is what, which are the most important classes, how many things I have of this class and that class is, I mean, you can of course do endless sparkling, but that's not the fastest thing on earth. So we did this visualization that helps us see the biggest classes and their subclasses. So you can say, well, agent, what's that? That's actually the superclass for organizations and people. And then, well, people, how many people I have? I immediately see that I have 1.3 million people in this data set. I get some samples, I see the subclasses. Organizations, well, fine, I have like 300,000 organizations. Get some samples, see that actually plenty of those are sports teams, 34,000, and only like 70,000 of those are companies, and so on and so forth. So that's this kind of tooling that if you have the kind of knowledge graph that I'm showing, you absolutely need it to be able to figure out what's in there. And even more, like being able to figure out what are the typical connections between classes. So you see that in this data set, it turns out geographic features are most heavily interconnected with other things, be it with documents or with people. And then you can easily click and analyze what are the most typical relationship types between a geographic feature and a person. And then you see 5 features. Say, okay, then probably I did the mapping wrong. This shouldn't be here. But you need the tools that allow you to very easily spot these distributions in your data. So much about it. This was the story of what it takes and what kind of tooling you need to put a big knowledge graph together. And the question, what do you do with this big knowledge graph? One of the use cases I'm presenting is, well, what a colleague of ours, Jem Rayfield, defined as dynamic semantic publishing, like back in 2010. And the concept was, imagine you have tons of content. In this case, the first project they did was for the World Cup, Soccer World Cup, Football World Cup 2010. So they had a knowledge graph with all the players, all the teams, all the groups, referees, whatever. And they use, again, this kind of technology to annotate, to link, to tag all the content that comes related to this event with references to these concepts. And then when you go to the website, they were maintaining 800 web pages about each entity in this knowledge graph, each player, each team, each group, everything. So did any of you went to the BBC website back 2010? Yeah, I see some people nodding. If you go there, you can go to the page for Frank Lampard, and it is actually populated with, there is a template for players, and it is populated with probably 5 Sparkle queries for this one that fetch relevant content and some data and pictures and this kind of stuff. So that's one possible usage of this technology in publishing media. And there are reasons why people prefer RDF, Sparkle and the related technology stack compared to property graphs and Cypher. The major reasons are that for scenarios like enterprise data integration, master data management, metadata management, data publishing, RDF does have a number of advantages. The most obvious one being standard compliance. Then if you do master data, you want to have a schema language, and that's something that you actually don't have if you use property graphs, because the emphasis there was always on analytics on graphs that come and go. So you got a big graph, live eventually, you search some patterns in it and you drop it. But then what if you're in the use case of maintaining a big knowledge graph of essentially master data, concepts that you care about, and then annotating your precious content against this knowledge graph. Then being able to do proper data governance, to have all sorts of schema validations and stuff is really important. And these set of standards that you have around RDF and Sparkle actually allow you to do so. Then the other advantages come from like, by design, having globally unique identifiers, having a lot of linked open data. And actually many of the engines, including GraphDB, have optimizations that allow you to very easily make clusters of identifiers which are information about the same entity coming from different sources, which actually makes data linking and data fusion much faster as compared to a situation where you don't have it. And in a way, it's an HO fit for knowledge graphs, because most of the knowledge graphs, I believe, are master data. Be it global master data, the way Google uses it, be it Microsoft Inc. or something else. But these are reference structures, master data, or reference data structures that you want to reuse. At least, I believe that's the prevailing thing. It's not that each graph is a knowledge graph, at least not to my interpretation. And of course, there is logical inference. One should be careful using it because it's quite easy to get into performance issues and complexity issues. But again, the best practices of using it, people know what it takes to scale with their benchmarks, which allow you to see how this combines with other features and so on and so forth. So one of these benchmarks is Linked Data Benchmarking Council's Semantic Publishing Benchmark. LDBC is actually organization. I'm on the board of LDBC. Ourselves, OpenLink, Neo4j, Oracle, IBM. Quite a number of the players in this field where we define benchmarks for, well, in 3 areas, for like RDF-based engines, for property graph-based engines, and there are some benchmarks for graph analytics for people like IBM who actually don't care so much about what language you're using. It's more like offline analytics tool, non-transactional. So one of these benchmarks is precisely based on this use case of BBC. So you have a big knowledge graph, you have a lot of metadata, and then there are two streams of activities. One of them is updates, because if you have a sport event running, you have tons of stuff happening in parallel. So you have a big number of updates in parallel. And then the other thing is they call it aggregation queries, which is fetching this data that you gotta publish on the website or somewhere else. So for those, the typical load on a really big installation is tens of updates per second, and for these you have like hundreds of read queries per second. And there's some benchmark results. Just on a single node, you can see that we can, if you have like, I don't know, 10 reading agents and 8 agents that do updates, or 4 agents that do updates, you can get to, out of a single box, with 20 gigs of RAM, you can get to like 60 reads and 8 or 9 updates per second. We got recently quite a number of questions from our clients how this compares to Neptune, and we've been talking to the team there and asking, yeah, is there something that we can do better? We try to do as close comparison as possible. We showed them the results, we showed them the setting, asked whether we can do something better. The only answer was, well, you should probably get a bigger instance. Okay, I know I can get a bigger instance. But the baseline is that, yeah, out of the box loading is like 5-6 times slower. Queries are 8 times slower for Neptune. So what it takes to get to this level of performance and back these kind of scenarios for like media or big publishers, really using this as a transactional engine to deal with your metadata and master data. Well, it takes features like, of course, high availability clusters. Integration with full text search is very important. We integrate with Lucene, Elasticsearch, and so on, and quite a number of other things. So I don't have the time to go deep into all sorts of features. That there is complex architecture that allows you to do multi-DC installations with integration with clustered full text search engines and so on and so forth. Good. I have a few minutes, so I'll tell you a bit about why we care about global data, and I'll do the demo, and I'll stop. So, essentially, we believe that most of the businesses in a economy that is getting more and more globalized and interconnected need to deal with global data to make the right decisions. So they should combine their own data with global data, and that's not easy. It's not easy to match information about one and the same company, your client that comes out of your CRM system, and a company database that you bought from somewhere else. Identifying entities in text is, again, another task that is not easy to do. So we've been specializing in doing these kind of things in one of the domains with persons, organizations, and locations, because you have this in common between many business applications, and open data is getting more and more available in this space. So we believe that in the coming years, dealing with global master data, so taking global company data, locations data, people data, will be a de facto standard, and you will not be competitive. Your business will not be competitive unless you can integrate this data with your CRM system or whatever, and take some insights. So the trickiest part of this is how you do this integration, how you figure out that the Tim Cook that is mentioned in this specific document is the CEO of Apple and not the football player. And this actually requires a lot of the kind of knowledge about entities and concepts that people have and machines don't have. The kind of awareness of what Tim Cook is and what Paul Appleby is, and what Connected Data London is. So it's a combination of different things, like being able to know what the differentiating features are, what are the similar concepts, how important is one feature, what are the related features, what are the co-current features. The combination of all these things is what people mean when they say, I'm aware of something, or I'm cognizant of something. And it actually takes combining data from different sources to get it right, and actually big volumes of data. And I'll finish off with this, I call it awareness game. So I have questions for you. So we'll start off the interactive session, and then we'll see how the machine does it. So let's start with the easy ones. Important airports near London.
Heathrow, City, Stansted.
Yep.
Gatwick.
Okay, so In this, yeah, the network is probably a bit slower than it has to be for this purpose. So we have sample queries where you can play with quite a number of these things. I'll be done in a couple of minutes, hopefully. If it goes too slow, I'll have to drop the demo part. Okay, so we have a sample query that essentially says, get the geographic coordinates of an entity, in this case, London, and then get nearby entities within 50 miles. Can you guess how many airports are there within 50 miles of London? How much? 8?
8 or 9. No. I know.
You've got all the small ones like Biggin Hill and Red Hill and...
Okay, you have 84. You have 84 of them. So figuring out which of these 80 are the ones that you care about and which are those that you don't care could be a problem if you have a knowledge graph that tries to cover it all. So one of the cognitive analytic features is something we call Rdf Rank. So for each of the airports that we get here, we get the rank, and then we actually sort them by rank. And that's the reason why Heathrow, Gatwick, Stansted, City Airport, and Southend get at the top. And that's a generic, essentially, ranking technique. It's like PageRank implemented on an RDF graph, and that's part of the engine. So you get it for free. You just won't have to say I want it, and it's being computed, and you can use it in Sparkle queries. You can get like suggestions to see that it's not fake. Yeah, tell me any other city that you want to check. Any. Paris is an easy one. If I'm not sure how to spell Paris, I can get suggestions. And then there you go. Is it right? Yeah. Yeah. Okay, and then you can do it for all sorts of entities also. So, sorry. You can get the best universities and education institutions. So it's really like not just airports made up for the case.
So this ranking is made automatically through the...
Yeah. It is automatically computed using PageRank on the RDF graph. You can tune it. You can say, I want to ignore these properties, and I want to ignore that classes. But out of the box, it goes to everything.
You just need the data and do the rank for...
Sorry?
You just needed the data.
Yeah.
Some data
Yeah.
How is it ranked? I mean, is it location? Is it number of instances? Or?
It is like Google's PageRank. So it is how many other entities refer to this one and how important are they? Very same like the web pages.
And the relationship near there, is that just a spatial query?
We have a geospatial indices plugin, so you can efficiently calculate nearby rectangles, these kind of things. Yeah. Okay, so I'll do my favorite one, and I'm really done. So companies similar to Google. So without asking what it means to be similar, businesses that are similar to Google, what would be your first reaction? Your first reaction, Microsoft?
Oh, there are quite a few now, like the Go, there are many search engines now.
Amazon. Okay, so and that's based on analytics on the graph of how similar the descriptions of these entities are in the graph. And you automatically get Facebook, Yahoo, Apple, AOL, Microsoft. Make sense? Okay. And that's an example of like 2 or 3 types of analytics, like similarity and importance and few other things, popularity. Okay, thank you.